Okay, so you've probably been hearing these terms everywhere lately, right? AI agents, agentic AI. I mean, the search trends really took off late 2022. But what are they? Are they, the same thing, just new buzzwords? And maybe more importantly, why should you even care? Today, we're doing a deep dive. We've got some really fascinating source material here. It's a critical review paper that, well, it tries to structure this whole area, maps out the applications, the challenges, all that. So our mission today, cut through the hype. Let's understand what these terms really mean, see where they're popping up, and maybe get a sense of the big hurdles and what's next. Think of it like your shortcut to getting up to speed on some cutting-edge AI stuff.
Yeah, and I think what's really crucial here, and the paper points this out, is that this isn't just semantics, splitting hairs. Understanding the difference between a standard AI agent and an agentic AI system, it's actually fundamental. It affects how we design them, how we evaluate them, even how much we can trust them as they get, well, more complex. It really is a pretty significant evolution in AI capabilities we're seeing.
Absolutely, a definite progression. So here's the plan. We'll start with the basics AI agents, how they evolve from generative AI. Then we'll jump into the more complex stuff, agentic AI, compare them directly, look at some pretty cool real-world examples, and then, yeah, tackle the tough parts, the challenges, the potential fixes. Sound good? All right, let's jump in. AI agents, how does our source material define them? What's the core idea?
Okay, so at its heart, the paper defines an AI agent as basically an autonomous software entity. Its whole purpose is goal-directed task execution, right? But typically within a sort of bounded digital environment. Think of its core loop. It perceives inputs, sees what's going on, it reasons over that information, and then it initiates actions to hit some objective. Often they act like surrogates, maybe for a human user or even another piece of software. The key traits highlighted are autonomy for its specific job, task specificity, and being reactive, but also crucially adaptive.
Okay, adaptive. So how's that different from, say, automation we've had for ages, like
Yeah.
simple scripts or older AI?
That's a really good point. The difference is adaptability based on dynamic inputs.
Oh.
So unlike a deterministic script, which just follows preset rules, or even earlier um, expert systems or reactive robots, these modern AI agents, they can adjust their plan or actions on the fly because they're reasoning about the information they perceive now, not just following a fixed path.
And what's giving them that reasoning power, that adaptability?
It mostly comes down to foundational models, primarily large language models, LLMs, the GPT-4s, Claudes, Llamas of the world. They're the core reasoning engine. They understand the goal, process info, plan the steps. But the source also mentions large image models. LIMs are increasingly important too. Think C-like, B-like 2. They give the agent eyes, basically, visual perception.
Okay.
So an LLM might figure out what to do, and a LIM helps it see the situation. The paper gives an example, like a drone identifying diseased fruit using a LIM. And usually these models are accessed through APIs, like from OpenAI, Google, Hugging Face.
Right. Now, before agents, we heard tons about generative AI. How does that fit in? Is it just a different name for the same thing, or?
No, definitely not the same thing. And this is where the paper draws a really clear line. Generative models, the ones creating text, images, code, they're essentially the precursor technology. They're amazing at generating content based on a prompt. So the reactive, yes. But fundamentally, they lack things like an internal state that persists, or long-term memory, or the built-in drive to pursue a multi-step goal within an environment on their own. They create stuff, but they don't act autonomously to achieve an objective in the same way an agent does.
Okay, so AI agents take that generative power and add the ability to actually do things, to interact.
Exactly. They build right on top of those generative models, usually LLMs. They augment them with the necessary infrastructure to become, well, functional actors. This means adding things like tool use, the ability to call external APIs, run code, search the web,
Right, using tools.
and sequential reasoning to break down tasks, memory buffers to hold context, planning routines. You see frameworks like React, which is interesting because it combines reasoning and action steps iteratively.
Okay.
Early examples like AutoGPT or Baby AGI really showcase this using an LLM as the planner and executor. And there are tool-augmented systems too, like EasyTool, Gentopia. It's this combination of the LLM brain, the tools as hands, plus memory and planning structures that turns a static generator into a dynamic task-completing agent, like AutoGPT planning market analysis using web searches.
So if you had to boil it down, what's the key takeaway about these standard AI agents?
I'd say it's their high autonomy within a specific task, combined with that ability to leverage tools. They aren't AGI, not even close. But for their narrow scope, they can operate pretty independently thanks to the foundational models and the tools they can call. They're like specialized digital workers.
Okay, specialized workers. Got it. But if they're already so capable with the tools for specific tasks, why the shift to talking about agentic AI? What's the next step here?
That's where the paper talks about a paradigmatic shift. It's driven by the limitations of single agents. When you have really complex goals, things that need multiple steps or different kinds of expertise, a single agent often struggles. Agentic AI isn't about just one agent anymore. It's about multiple specialized agents working together, collaborating to achieve a much larger, more complex goal.
Multiple agents collaborating. That sounds potentially chaotic. How does that coordination actually happen? What makes it a system?
It's a fundamental architectural difference. It's moving from that single perceive reason act loop for one task to orchestrating a whole system of agents. Key features here are things like goal decomposition, breaking the big goal into smaller, manageable subtasks, dynamic task distribution, figuring out which specialized agent is best suited for each subtask and assigning it on the fly, multi-step reasoning and planning across the agents, adapting as things change. And crucially, inter-agent communication. They need ways to talk to each other, maybe direct messaging, maybe through a shared memory space. Plus, there's often a layer of reflective reasoning and persistent memory for the whole system, so it can track progress, learn from what's happened, and refine the overall strategy. It's about building intelligence at the system level, not just the individual agent level.
The paper used a smart home analogy, which I found helpful. Can you walk us through that again?
Yeah, that's a great one for illustrating the jump. Think of a single AI agent like your smart thermostat. Its job: manage the temperature in one room or zone, perceives the temp, reasons about your setting, acts by switching the heating or cooling. It works alone.
Right, isolated task.
Exactly. Now, Agentic AI is the entire smart home system. You've got a weather agent checking the forecast, an energy agent monitoring prices, and maybe solar panel output, a security agent knowing who's home or away, a scheduling agent managing calendars, and the thermostat agent. They all communicate and coordinate. Maybe the weather agent sees a cold snap coming, the energy agent knows electricity is cheap overnight, the scheduling agent knows you'll be home late.
Ah, so they work together.
Right. They coordinate to preheat the house efficiently before you arrive, or adjust settings automatically when the security agent says the house is empty. It's not just automating one device, it's orchestrating multiple specialized functions towards broader goals, like comfort, efficiency, security. That requires that interaction and shared understanding. It's adaptive, orchestrated intelligence.
That really clarifies the difference. Okay, let's nail down the core distinctions then. If we put a single AI agent and an agentic AI system side by side, what are the absolute key differentiators according to the paper?
Okay, let's break it down based on the source. First, autonomy scope. An AI agent has autonomy, sure, but it's within its specific task. Agentic AI aims for higher system-level autonomy, managing complex, multi-step workflows that might span different domains.
To a broader scope.
Exactly. Second, task complexity. AI agents handle single specific tasks well. Agentic AI is explicitly designed for complex, multi-step objectives that inherently need coordination, things one agent can't easily do alone.
Right.
Third, collaboration. This is maybe the biggest one. An AI agent typically works independently, maybe using tools. Agentic AI is defined by multi-agent collaboration and information sharing. It has to happen.
Collaboration is key.
Fourth, architecture. An AI agent is often, an LLM plus some tools and maybe memory. An agentic AI system is inherently a multi-agent architecture. It has to have multiple agents, orchestration layers, often shared memory. It's structurally different.
Different blueprint altogether.
Yes. And fifth, mechanism. How they get things done. An AI agent uses tool calling, function execution, maybe some planning. Agentic AI relies on inter-agent communication, coordination, and collaborative problem solving as its core operational mechanism.
Okay, so that architectural difference seems really central to enabling the collaboration. It's not just making one agent bigger, it's building a structured team.
Precisely. The paper really emphasizes these architectural enhancements needed for agentic AI. Things like an ensemble of specialized agents. So instead of one generalist, you have maybe a planning agent, a research agent, a writing agent, a validation agent. The paper mentions MetaGPT using corporate roles as an analogy CEO, programmer, tester agents.
Like a mini company.
Kind of. Then advanced reasoning and planning, often using more complex techniques like tree of thoughts or recursive planning to handle those multi-step dependencies. Persistent memory architectures. This is huge for coordination. Shared memory spaces, episodic, semantic, vector stores allow agents to stay synchronized and build on each other's work. Think Autogen scratch pads for sharing context.
Shared context is vital, yeah.
And maybe most characteristically, orchestration layers or meta agents. These are components, sometimes agents themselves, whose job is explicitly to coordinate the others, assign tasks, manage data flow, resolve conflicts, keep the overall goal in sight, like the chat dev virtual CEO example.
So it really is like building an AI team complete with specialized roles and an AI project manager overseeing everything.
That's a really good analogy, yeah. It's about distributing the intelligence and managing complexity in a way that hopefully requires less moment-to-moment human guidance than trying to get one agent to do everything.
Okay, let's ground this. Where are we actually seeing these things used? Let's start with the single AI agents. What are some concrete examples from the source?
Right, the paper gives quite a few examples, usually focused on automating specific, well-defined tasks. A big one is customer support and internal search. Chatbots handling common questions, systems that help employees find info in company docs using natural language, tools like Salesforce Einstein, Intercom Fin, Notion AI fit here.
You see those a lot.
Then email filtering and prioritization. Things that automatically sort your inbox, maybe suggest replies, flag urgent stuff. Outlook's features, superhuman.
Lifesavers sometimes.
Definitely. Also, personalized recommendations and basic reporting, Amazon suggesting products based on your browsing, or tools like Power BI Copilot generating charts from a simple request, Tableau Pulse 2,
Okay.
and autonomous scheduling assistants. Those tools that integrate with your calendar and Slack, find meeting times across time zones, maybe learn your preferences, like X.AI, Reclaim AI, Clockwise. The pattern is clear. Automating a specific bounded job to make things more efficient.
Makes sense. Very practical stuff. Now, what about agentic AI? Where are these more complex collaborative systems showing up, the ones coordinating multiple agents?
Agentic AI applications, as you'd expect, are tackling problems that demand that coordination. One area highlighted is multi-agent research assistance. Imagine automating something complex like writing a grant proposal. You could have one agent finding relevant papers, another summarizing them, another drafting sessions, another checking for alignment with requirements, maybe another formatting, all coordinated by an orchestrator agent using some shared memory. Frameworks like Autogen or Crew AI are used for this kind of thing.
Wow. Okay. That's complex.
Yeah. Or intelligent robotics coordination. Think of a warehouse or maybe harvesting crops. You need different robots doing different things, mapping, picking, transporting, but they all need to work together. Share information about the environment like a shared map and adapt dynamically. MetaGPT's concepts could apply here.
So coordinating physical actions.
Exactly. Another potential area is collaborative medical decision support. High stakes, obviously. But you could envision agents specializing in diagnostics, patient history retrieval, treatment guidelines, drug interactions, all feeding into a central system that helps clinicians make more informed decisions, especially in complex cases, like in an ICU. Needs careful validation, of course.
Huge potential, huge risks there too.
Absolutely. And then multi-agent game AI and adaptive workflow automation, creating really complex, believable non-player character interactions in games, or automating sophisticated business processes. Like cybersecurity incident response, you might have agents classifying threats, correlating logs from different systems, checking compliance policies, even simulating mitigation strategies, all managed by an orchestrator. Tools like AI Dungeon for games or Multion, Cognosis, Autogen, ChatDev for workflow and code generation fall into this broader category.
The jump in complexity is really stark there, from scheduling a meeting to coordinating a whole research paper or a robot fleet.
Yeah, it's a significant leap in capability and ambition.
But, complexity usually means challenges. This sounds incredibly difficult to get right. What are the big hurdles the paper points out? Let's start with the single AI agents. What are their main limitations?
Yeah, even the simpler single agents face pretty significant challenges. Many stem from the underlying LLMs. A huge one is the lack of causal understanding. LLMs are amazing pattern matchers, finding correlations in data, but they don't grasp cause and effect in a deep way.
Right. Correlation isn't causation.
Exactly. And this makes them brittle. If the situation changes slightly from their training data, what researchers call distributional shift, they can fail unexpectedly. The paper mentions research on this. A navigation agent trained in sunny weather might just break down in snow because it doesn't have a real model of traction, just correlations it learned.
Okay, that's a big one.
Then you have the inherited LLM limitations. Hallucinations, making things up, which is dangerous and feels like medicine or law. They can be super sensitive to how you phrase a prompt. Their reasoning, even with clever prompting like chain of thought, can still be surprisingly shallow for complex problems. Plus, they're costly to run, can have latency issues, and their knowledge is often frozen in time unless you use RGA. And biases in the training data get reproduced.
All the usual LLM complaints, basically.
Pretty much. Also, incomplete agentic properties. Compared to the theoretical ideal of an agent, they're often more reactive than truly proactive. They struggle with long-term goals, real-time adaptation can be slow, and their social interaction ability is often very basic or scripted. They also show limited long-horizon planning and recovery. For tasks with many steps, or ones needing consistency over time, they can struggle. And when they fail mid-task, they often don't have good mechanisms to figure out why and recover gracefully. They might just stop or repeat the mistake.
Silent failures are bad.
Very bad. And finally, reliability and safety concerns. Simply put, they're not reliable or verifiable enough for critical systems yet. Their behavior can be unpredictable, it's hard to interpret why they chose a certain plan, and there are no formal safety guarantees. Big barriers.
Okay, those are definitely significant hurdles for single agents. And now, agentic AI, does adding more agents just make all those problems worse or introduce new ones?
Yes, both, unfortunately. Agentic AI amplifies many of the single-agent issues and brings a whole new set of coordination-related challenges to the table. The amplified causality challenges are a nightmare. Now you have multiple agents influencing each other and the environment. Misunderstanding cause and effect can lead to cascading failures. One agent's error poisons the well for others. Figuring out causal links in these dynamic interacting systems is really tough.
Air cascades, yeah, I can see that.
Communication and coordination bottlenecks.
Yep.
Getting agents to talk efficiently and understand each other is hard. Natural language is ambiguous. How do you ensure they're aligned on goals? How do you manage shared resources without conflicts or deadlocks? We lack robust, standardized protocols for this.
The Power of Babel problem, but for AIs.
Sort of. Then there's emergent behavior and predictability. When you have complex interactions, the system can start doing things you never intended or predicted. Sometimes useful, sometimes harmful or unstable, like getting stuck in loops or contradictory states. And debugging is a nightmare because the LLMs are opaque, and now you have multiple opaque agents interacting.
Finding the bug sounds impossible.
It's incredibly difficult, which leads to scalability and debugging complexity. It's not just harder, it's exponentially harder to trace problems through chains of interactions across black box agents. Adding more agents doesn't always help. Poorly orchestrated, they can just add noise. Trust, explainability, and verification are compounded. If explaining one agent is hard, explaining a collective decision emerging from multiple interacting agents is way harder. There's often no unified log or way to trace reasoning across the system. Huge barrier for adoption, especially anywhere safety matters.
Can't trust what you can't understand or verify.
Exactly. And security and adversarial risks multiply. More agents, more communication channels mean a larger attack surface. Compromise one agent, and it could potentially spread bad data or malicious commands through the whole system via prompt injection or corrupted state. The dynamics themselves might be exploitable. We lack security frameworks specifically for these multi-agent systems.
Scary.
And finally, ethical and governance challenges. Accountability gets fuzzy. Who's responsible when a multi-agent system messes up? Biases can get amplified as they bounce between agents, and there's the risk of value drift it takes. Agents optimizing their local tasks might diverge from the overall human intent. Current alignment techniques struggle with these collective dynamics. We need new governance approaches built in.
Wow. Okay, that's quite a list of challenges. It really underscores that agentic AI is not just more agents, it's a whole new kind of system with unique problems.
Absolutely. And the paper also notes that the foundations are still immature, lack of standard architectures, ad hoc protocols, big research gaps, especially around scalable causal reasoning and verification.
But it's not all doom and gloom, right? The paper does talk about potential solutions. What are researchers working on to tackle these massive challenges?
Yes. Thankfully, there's a lot of active research, and the paper outlines several promising directions. Many build on ideas from single agents, but adapt them for the complexity of multi-agent systems. Retrieval-augmented generation, RAG, using external data to ground responses is key for single agents. For agentic AI, it becomes a vital shared grounding mechanism. If all agents pull from the same updated knowledge base, it helps keep them consistent and reduces conflicting information or hallucinations.
Shared source of truth.
Yes, exactly. Tool-augmented reasoning, function calling, is essential for giving agents capabilities. In agentic AI, this supports role specialization. Different agents can be equipped with different tools relevant to their specific function within the larger workflow.
Makes sense.
The agentic loop that perceive, reason, act, observe cycle, like in React, is fundamental. For agentic AI, making this work collaboratively requires coherence. Agents need to observe not just the environment, but potentially each other's actions or outputs, often mediated through shared memory or logs, to adapt effectively as a team.
Tighter feedback loops.
Yeah, memory architectures need to be more sophisticated than just short-term buffers. For agentic AI, robust distributed state management is crucial. Shared episodic memory, semantic memory general knowledge, vector stores for retrieval allow agents to maintain context and coordinate over longer periods.
The system's collective memory.
Right. Multi-agent orchestration with role specialization is a core design principle. Explicitly defining agent roles, planner, coder, tester, and having a dedicated orchestrator or meta-agent manage the workflow, dependencies, and conflicts seems critical for managing complexity. It also helps with interpretability and fault isolation. Models like MetaGPT and ChatDev embody this.
The AI project manager idea again?
Exactly. Reflexive and self-critique mechanisms are about agents checking their own work. For agentic AI, this can be extended to inter-agent evaluation. Maybe a reviewer agent checks the output of a writer agent. This builds in quality control to the collaborative process. The reflection pattern is related to this.
Peer review for AIs. Huh.
Kind of. Programmatic prompt engineering pipelines can help automate creating consistent and effective prompts. For agentic AI, this becomes important for ensuring scalable, role-consistent communication between agents, reducing ambiguity and coordination failures.
Standardizing the comms.
Yes. Causal modeling and simulation-based planning represents a push beyond just correlation. For agentic AI, incorporating causal understanding is vital for safe coordination, helping agents anticipate how their actions will affect others and the overall system state, allowing for more robust planning.
Planning based on cause and effect.
Crucial for safety. Monitoring, auditing, and explainability pipelines are about instrumenting the system. For agentic AI, comprehensive logging across all agents and interactions is exponentially more important for tracing problems, debugging, and building trust. Needed for any kind of regulation, too.
Got to see what's happening under the hood.
Absolutely.
Huh.
And finally, governance-aware architectures. This means building governance principles like role-based access controls, sandboxing agent capabilities, clear accountability structures directly into the system design across the roles and workflows, essential for safety, compliance, and responsible deployment.
It really feels like the solutions are heavily focused on robust system design, managing those interactions, building in checks and balances for the collective, all layered on top of improving the individual agents.
That's a perfect summary. The future roadmap outlined in the paper suggests AI agents will keep improving, getting more proactive, better tool use, maybe some causal reasoning, better safety. Agentic AI builds on that, but the big focus areas are scaling these multi-agent systems effectively, creating sophisticated but understandable orchestration, developing truly robust shared memory, using simulation for better planning, embedding strong ethical governance, and crucially, tailoring these powerful collaborative systems for specific high-value domains like law, science, or medicine.
So we've covered a lot of ground, from AI agents as these pretty capable task-specific tools, all the way to agentic AI systems envisioned as these complex, coordinated teams of specialized agents tackling really big goals. It's clearly a super fast-moving field, immense potential, but also, wow, some really significant interconnected challenges. Technical, safety, coordination. It's all in there.
Yeah, the source material really drives home that agentic AI isn't just, AI agents plus plus n. It's a fundamentally different beast. It's aiming for a form of collective machine intelligence. And that requires totally new architectural thinking, new coordination strategies, much more rigorous safety engineering than we needed for single agents.
And it seems the more autonomous and integrated these systems become, whether in our software development or scientific research, maybe even controlling physical systems, the more urgent those questions become. Predictability, trust, explainability, governance. How do we manage these powerful collectives? Definitely a lot to think about. So here's a final thought for you, our listener, to maybe mull over. As we see AI shifting from tools you direct task by task towards potentially proactive, collaborative agents managing complex workflows, maybe with less direct supervision, how might you need to adapt? How might your way of working with AI need to change in the coming years? That's all the time we have for this deep dive. We really hope this gave you a clearer view into the exciting and, challenging landscape of AI agents and agentic